Hi folks! In this video we're going to deepen our understanding of what a definite integral is in a geometric sense. So in the last video we only saw functions that were above the x-axis, and that meant that area and definite integral basically meant the same thing. But area below the x-axis actually gets counted negatively. One way to think about an integral is that it is net signed area. That seems weird. So let's take an example here. If f of x is negative 2x, so that's just a line with a negative slope that goes through the origin. And I could figure out that right at this point here, this would be 2, negative 4. If what I wanted here was the area would be 1/2 base times height. The area would be 4 units squared. Okay, so I can put that here, 4 units squared. Let's go to the GDC and figure out what the integral is. I can hit Math, head down for definite integral. We could do this by actually looking at it, by doing it on the graph, but this is pretty slick too. Negative 2x from 0 to 2. You may have to type in dx. For me, it's already there. And it tells us, even though the area is 4, the integral is negative 4. And this is kind of like the difference between distance and displacement, or how many steps you've taken and your net change in position. An integral on its own is more like net change in position, or, like I said, net signed area. So if I were to evaluate these two geometric ones down here, if I wanted the integral from 0 to 6, I could figure out that this area right here is 6 full blockies, and then 1.5 for the triangle. So this is going to be 7.5. And this area over here, between the x-axis and the function, is also 7.5. But as an integral, it's going to be counted negatively. So the integral from 0 to 6, you could think of it as the integral from 0 to 3 plus the integral from 3 to 6, just adding those two parts together. And one of those is going to be 7.5, and the other one's going to be negative 7.5, for a grand total of 0. Or if you just looked at the green and the red, you'd say, oh, well, there's an equal amount of area above and below the x-axis, therefore the integral is going to be 0. The total area, if we asked for area, would be 15 units squared. Let's try this other one. So right here, I've got some stuff below the x-axis. Right here, I've got above. And right here, I'll do it in yellow, I've got some stuff below the x-axis. So if I wanted to find this full integral from 0 to 6, I'd have to figure out, okay, how much is that first red one? Well, it's 1/4 of a circle with a radius of 2, but it's counted negatively because it's below. We've got 1 full blocky and 2 halves, so that is 2 blocks above. And then finally, I've got a negative half here. So put that all together, that's going to give you negative pi plus 1.5, okay, which you could also find as a decimal as negative 1.64, I think. But it's better exact. And when you look at that question in B, it does look like there's more area below the x-axis than above. That's why the integral ends up being negative in the end. There's more below than above. That leads us to some definite integral properties. I think we'll start with the bottom one, because we already used the bottom one. In the very first question, when we wanted the integral from 0 to 6, we found the integral from 0 to 3, and added on the integral from 3 to 6. So if you have an integral from a to b, and then it meets up at b and it goes to c, then that is equivalent to the integral from a to c. I like to think of this as if you start in Alberton and go to Borden, and then go from Borden to Charlottetown, you've essentially gone from Alberton to Charlottetown. You have gone, you've had a stop in the middle, but in the end, your final destination is at C, and your initial point of emanation is at A. There are some other properties here. The integral from A to A, imagine that. If you wanted to find the area from A to A, that's going to be 0. If there's no width, there's no area. Then there's also no net signed area. One nice property is that you can pop a constant out front. So if you have something unpleasant like Avogadro's number involved, you can deal with that at the end. All right, we've already seen that this idea of area only sort of works for an integral. Area below is counted negatively. We never say negative area because that doesn't really make sense. We could also think of something called like backwards area, starting at the right endpoint and ending at the left. And again, that seems like a weird thing to do. So instead of going from A to B, we're going from B to A. What that is going to do is change this from negative to positive or positive to negative. You'll just get the negative of what you would have got from, quote, forward area. And again, this does seem probably pretty weird to think of it in terms of area going one way or the other. So integrals are not quite area. We'll deal with why that's the case when we get to the fundamental theorem of calculus fairly soon. But just know if you switch the order of the boundaries, it changes the sign of the whole thing. And then our last property that we'll use is that if you have the integral of a sum or difference of functions, then you can split it apart into the sum or difference of the integrals of those functions. And that was true with limits as well. And it was true with derivatives. So most of these rules are pretty similar to what we would get with derivatives, sort of adapted. So let's play a little logic game here. We know some things about f of x, and we know some things about g of x. We know one little thing about g of x. So we want from 3 to 7 on f of x. Here's the property you might use. From 0 to 3 on f of x plus from 3 to 7 on f of x is equal to from 0 to 7 on f of x. Anytime you're trying to figure out what's going on at different boundaries. And that is really the fifth integration rule. And once I know that, I know that this part here is just the number 4. This is what we're looking for. And from 0 to 7, well, that's just the number 9. So in the end, the integral from 3 to 7 has to be 5, because 4 plus 5 makes 9. That's essentially what it is. 4 plus 5 makes 9, therefore the answer is 5. If you want to do it with less work, absolutely, be my guest. All right, next one. There's a rule that you can pop a constant, and a negative out front is just a constant of -1 that you're being multiplied by out front. Okay. So this is just going to give us negative, and what the integral normally would have been, -4. The other way you can think of this is that, if f of x had a net signed area here of 4, if you changed it to negative f of x, well, that flips it through the x-axis. So of course its integral is now going to be -4. Hopefully our rules in algebra and in calculus are consistent with each other. All right, the next one. The order of the boundaries has changed. This is rule number 3, rather. So this is just going to be the negative of what we'd get with the boundary the other way around. And so that's -4, just like it was in the second question we did here. All right, next one. We can split these apart. So we could call it 2f of x dx minus the integral from 3 to 7 of g of x dx. And again, you can pop a constant out front. And you probably have an intuitive sense of what the answer is going to be. And chances are you're correct if you just use that intuition. But I'm showing the properties that are at play here. So the integral from 3 to 7, we actually found it over here. It's 5. And the integral from 3 to 7 on g is up here. That's -1 for a grand total of 11. Notice that we never know what the functions f and g actually are. Let's keep pushing for a couple of more complicated ones here. So in this one, we've got f of x minus 2. It has moved right 2. But notice here that the boundaries have also moved right 2. So this should actually be equal to the integral from 0 to 7 on the basic function. If everything's moved right 2, well, then you have the same geometry happening. And the integral from 0 to 7 on f of x, let's check it out, is 9. So this is a way that we can connect with some of our function transformation stuff. I mean, similarly over here, I know that I can split this apart. 3 to 7 on g of x dx plus the integral from 3 to 7 of 5 dx. Weird. Okay, that first one from 3 to 7 on g of x is going to be -1. That's right up here. But this one, this was tricky. I mean, so let's imagine, what if you had y equals 5, and you were looking for the integral between 3 and 7? You'd essentially be looking for this area, and it would be positive in this case, and it would be a rectangle that is 5 by 4. So this integral would be 20 by thinking about it geometrically, okay, as the function y equals 5. What's the area under y equals 5 from 3 to 7? It's 20. So we get 19 as a final answer. Now, notice here that we may end up with other sort of more algebraic ways of approaching this, but there is this geometric interpretation. All right, one last one. We've got a sum. We've got a weird boundary. I'm going to split this apart as 0 to 7 on f of x and 0 to 7 on g of x. And I know that that's equal to 18. That's kind of helpful, but I don't want the integral from 0 to 7 on g of x. One thing I can do, though, is I can rewrite the integral from 0 to 7 on g of x as the integral from 0 to 3, which I want, plus the integral from 3 to 7, which it turns out I know. And now we can plug and chug. F of x from 0 to 7, if you check out the last slide, that was 9, plus 0 to 3 is what we're looking for. And then we have plus the integral from 3 to 7. Let's check that out. On g of x, that's -1. And that equals 18. So in other words, let's move this over. That means I have on my left-hand side, I have 8 plus the integral from 0 to 3, g of x dx equals 18, or the integral that we're looking for has a value of 10 without ever knowing what that actual function is. So in this case, we've just got little logic puzzles that we're playing with to get a sense of those integral properties. The big idea for this section is that the definite integral is related to the exact area under a curve, but area below the x-axis is counted negatively. And as long as you see a dx there, we're counting area between the function and the x-axis. There's some practice questions here on page 449. Number 12 is a great question to get you thinking about function transformations. I hope this has been helpful. Good luck with the material, and take care.